Okay, folks, in this video, I'm going to get a little bit descriptive, a little qualitative. I'm discussing three different materials, water, CO2, and helium, and we're going to look at each of their phase diagrams and talk about some cool stuff as a result of differing phases. So, and you also notice I've got a video down there in the corner that's going to help me supplement the discussion of CO2 and helium. So first, let's check out the H2O phase diagram. And the first thing that I want to point out is it is a humongous scale of pressure here, right? Starting from 1 Pascal all the way up to 1 terapascal, which recall, that's 1 times 10 to the 12th pascals. So because of this large range of pressure, that is on a log scale. So those things, right, 10, 100, 1,000, 10,000, right, they're going up by powers of 10. So that's why these curves just look a little bit different than the way that we might get used to seeing a phase diagram drawn out, you know, kind of in this like picture right here, or sometimes we see it look like this. So it's a little bit different looking because of the log scale. So let's find atmospheric pressure. So you can see there it is, 1 bar or 100 kPa. And if we notice there, when we scan down that pressure, excuse me, fighting a yawn, at 1 atmosphere, right, when we cross the vapor-liquid line, that would correspond to boiling, which of course happens at 100 Celsius or 373. So if we kept lowering the pressure, right, we would get now to the liquid solid line. And of course, we recognize that happens at 0 degrees. And of course, if we weren't at exactly 1 atmosphere, maybe we were a little less or a little more, you can see now that those boiling points and freezing points are readjusted. And what should be noticeable here is that the boiling point responds quite sensitively to changes in pressure, but the freezing point doesn't change as drastically, right? So that freezing point of 0 degrees stays pretty rock steady through a large range of pressures once we're at the triple point, right? We notice below the triple point, the vapor solid line, right, that's no longer freezing, rather that is the sublimation line, right? The boundary between the vapor and the solid. What I also want to point out specifically about water, this slope right here is negative, and that is indicative of a solid whose density is less than the liquid. And water is a rare one, and we're going to get into that in a little bit more detail soon. But this notion of the slope going back, so going to lower temperatures as pressure increases, that's a very rare thing. Typically, freezing points will increase with increasing pressure. I'll also point out here within the solid phase, you can see several different types of solids indicated by their crystal structures. So all of these different things, like maybe you've heard of ice 9 before, ice 7, and so on and so forth. These are all different types of interesting ice structures. And then the last thing I'll point out that maybe you noticed is this critical point. And yes, that critical point corresponds, oh my gosh, I'm not going to edit it. I'm sorry. Sorry for the yawn. More coffee. That critical point corresponds to PC, TC, and VC, the very same that we calculated in the van der Waals loops. Okay. And I'm going to show you a fantastic video related to what happens at this critical point in the next slide when I describe CO2. Okay, so let's take a look at the carbon dioxide phase diagram. So now notice here, this is over a much smaller scale. So this is a linear scale, so there's no log there. And you'll notice now it does have more of that classic phase diagram look to it, right? I often like to call that the flux capacitor. Shout out there to Back to the Future. So there's our triple point. And now what's really interesting with this So when you look on this scale here, atmospheric pressure is like way down there. So if you've ever played with dry ice, or if you've ever gotten to, observe some dry ice, you notice that it sublimes. It just directly goes from the solid phase to the liquid phase. And that's because if you notice here, atmospheric pressure, I'm actually going to erase these lines here because it's making it hard to see. So that was fun tracing it. Now I'm going to untrace it. If you look at the triple point there, the triple point is 5 atm. Well, 1 atm is like way down here. So if you're at the solid phase and you heat it up, you go directly to the gas. So the solid does not cross the liquid line at atmospheric pressure, which is why we observe dry ice to sublime at room conditions than melt. Or similarly, why we don't readily see liquid CO2 in typical room conditions. So now I'll also point out the critical point here, which for CO2 occurs at a very convenient set of conditions. So 31 Celsius and 73 atm is not difficult to get to experimentally. And beyond that, we have what's called a supercritical fluid. So supercritical fluids are fluids where the gas and the liquid have the same density. So it's a really interesting type of phase. And as it turns out, supercritical fluids are excellent solvents. And CO2, notably, is an excellent organic solvent when it's supercritical. So it's excellent at dissolving polar things. It's excellent at dissolving nonpolar things. And it is used routinely in the alcohol and cannabis industry to extract things out of those plants. So you can extract, of course, THC using supercritical CO2. You can also extract different flavors out of plants that you can use for, like different flavored things, whatever you would want to flavor something with, right? So it's an excellent organic solvent. So I'm going to play this video from Applied Science where he's built an apparatus to not only liquefy CO2, but then to make it go supercritical. So we're going to take a look at this video, which is pretty awesome.
CO2 is starting to boil in there.
And notice here, that's the actual temperature, right, of that apparatus. So you can compare that to our scale there. So he's getting into that supercritical.
Okay, now the boiling has pretty much stopped. You can still see some density changes in the liquid there, but at this point there's no more bubbles, and the transition from the liquid to the gas phase in there is almost gone. So let me give it another shake.
So it's gone supercritical.
As you can see, something interesting has happened. There's no more dividing line between liquid and gas inside there. So I'm going to unplug the heater. And give it a few minutes here is
Zoom it in a little bit.
CO2 has gone supercritical, meaning that the density between the liquid phase and the gas phase eventually became so similar that they blended together. So it's all one continuous phase in there now. Now to transition back, what I'm going to use is just a piece of dry ice, and I'm going to hold it against the aluminum on the outside here to bring the temperature down quickly. So check this out.
And there it goes. Now it's transitioning back to a gas and a liquid, which is kind of cool. So there you can see that.
Surprisingly, this actually works better with just water ice, since it melts and makes a nice contact between the aluminum and the ice cube. As you can see, we're back to two phases. So I built this.
Okay, and then I've got another little video here for the next phase diagram that I want to talk about, which is that of helium. Okay, so we can see here, this is another large scale on our y-axis, so that's definitely a log scale. You can see it going up by powers of 10. We'll note here that helium also has a critical point corresponding to PC, TC, and VC. But now you'll notice that there's this interesting thing going on here in this phase diagram called the lambda line. And the lambda line exists because it looks like a lambda, right? I can kind of draw a Greek letter lambda right there. So if we were to start at point A down here with gas phase helium, very, very cold gas phase helium, right at 3 Kelvin, and let it cool at a constant pressure, we would see it boil as we cross that line. And then eventually as it crosses this line, it will go into the superfluid phase, right? So remember, if I look back at the CO2 phase diagram, right, normally we would expect that to be the solid phase that exists here at low temperature and moderate pressures. But notice for helium, the solid phase is way up here. Notably, helium can exist in the BCC or HCP crystal lattices, which is kind of cool. But what's really special about helium is this superfluid. And what's amazing about superfluids is they have no viscosity. No viscosity. So they do some really interesting things. They will flow without any surface tension or any impedance as they're, trying to flow around an object or in a container. So in this video, we're going to see a couple different clips. And in one of them, it starts with a very porous, but very small, porous bottom beaker. And in that beaker, boiling liquid helium will not pass through the pores. The pores are too small. But as soon as it goes superfluid, the helium is able to just drip and pass right through the material as if it didn't even exist. So let's watch, and hopefully it'll be pretty amazing to you. So we can see right there, that's boiling liquid, right? Liquid helium at about 3 Kelvin. And it's getting colder and colder. And eventually we'll see it stop boiling because now we're square there in the middle of that phase. So right there, right when it stops, we're just squarely at point B. And then now this is showing you that, classic filtration device. And there it's boiling, and as soon as it goes superfluid, you can now see it dripping right out the bottom. So it is flowing without viscosity or any impedance at all. So this is pretty awesome. And then now we're going to see this container filled with superfluid helium. And you can see the little drops flowing there at the bottom. So because it has no viscosity, it just moves its way right over the edge and flows through. So this will also make a frictionless fountain. So if you could have a fountain of superfluid helium, it would just flow forever without ever, running out, assuming that you had a reservoir of it down there. So we're going to watch some more videos of this in the live lecture to get a better description. But I just kind of wanted to show you a couple videos of some more exotic phases that we're not used to seeing in our everyday lives. Okay, more on this in our live lecture meeting. I'll see you then.